All of our organizations are faced with increasing volumes of data, but how much of that data exactly do we need to use in our predictive analytics models, and at what point should we be worried that we might have to upgrade our modeling infrastructure? In this course, we will walk through the modeling process from start to finish and discuss how the amount of data fluctuates, often dramatically, at different stages of the project. IT or IT management, you're going to learn enough about the behind the scenes of building predictive models to understand exactly what kinds of demands these projects are going to put on the IT infrastructure. If you're a senior executive or perhaps in analytics management, this will give you a much deeper understanding of what critical choices are made regarding what data to use and when you will want to be part of that process. If you are a modeler, we'll review what at first appears to be some modeling basics, but from a point of view that doesn't get enough attention, and will be sure to give you new insights about effective modeling. Also, you would develop some critical skills to draw upon to more effectively collaborate with IT management, your own management, and senior management. I want to begin by reviewing some terms that will allow us to identify where we'll be focused in this course. My favorite definition of artificial intelligence is one that I'm going to borrow from a thought leader in this space named Colin Shear. A computer doing something that, if done by a human being, would be judged to be intelligent. Now, of course, artificial intelligence is a huge field and involves all kinds of things like visual recognition, driverless cars, and devices in our home like smart thermostats or devices like Amazon Alexa. We're going to be focused on traditional machine learning, which encompasses two of the most important topics of all, supervised and unsupervised machine learning. I'm going to define traditional machine learning in the following way: a broad term that generally refers to presenting carefully curated data to computer algorithms that find patterns and systematically generate models. These models are going to be in the form of formulas or rule sets. While the algorithms are explicitly programmed by humans, the models are automatically generated. We're going to be even more focused than that. Throughout the course, we're going to be talking about supervised machine learning. Supervised machine learning is going to rely upon a historical data set where some important outcome is known. So given a data set with a target variable and input variables, a modeling algorithm automatically generates a model, establishes a relationship between the target variable and those input variables. This allows us to make predictions, and that's supervised machine learning. Now we're going to do a high-level review of supervised machine learning, which essentially is taking historical data to build a model, which we then score on new data. So let's take a closer look. In our historical data, we have to have an established outcome. So if we're talking about loans, they've paid or perhaps they defaulted on their mortgage. We need that end result to be known. Then we need predictors. There can be numerous predictors. Hopefully we have dozens or hundreds of them. Examples could include things like this: whether or not the loan in question is their primary mortgage, or maybe it's a second mortgage, or what percentage of their income is being paid to housing. And this can help us predict that end result. So in order to do it, in order to map those predictors to the end result, we need a modeling algorithm. And modelers are experts in this, and there's going to be many of them that they might draw upon. They have names like decision tree, support vector machine, logistic regression, or neural network. There are dozens more. We're going to use that historical data to establish the model. And inside the model, it's just some kind of a formula, very frequently in the form of a rule set. Like if variable x is true and the value of y is less than 100, then we think that they might default. Now, the past data is the basis of that rule set or model, but we've got to score it on new data on a regular basis, every month or every night or so on. And this is going to produce a score. It's not just going to tell us default or not, it's going to give us a probability, like this. So we have just 4 loan IDs, and we have these scores, 6% chance, 80% chance, 1% chance that they're going to default. And we use that score to predict the end result. I'm going to identify 9 steps in the building of supervised machine learning models where you want to pause and ask yourself, what volume of data am I processing at this step? Store. First, you have to store the data and steward it so that the organization can access it as needed. Typically, when organizations come up with a big data strategy, they are focused almost entirely on the data storage aspect and assume that all other phases are done on the entirety of the data. It's simply not true. The volume of data will change dramatically from step to step in the process. Assess. The data scientist who is in charge of modeling has to have access to all of the data so that they can assess it. They can't be exactly certain of what they'll need until they take a good look. While the assessment is pretty basic, they might have to look at several years' worth of data. The most important thing that they're searching for is to figure out how much data do I need to build this model. The volume of data tends to start going down after this step. Select. The select step is closely tied to the business problem. For instance, you might be sending promotions out via email. Well, you might only analyze loyalty card customers if they're the only ones that you have emails for. The volume of data will tend to decrease dramatically during this step. Integrate. Based upon the assessment, the basic structure of the modeling data set takes shape. What often makes this computationally intensive is that in order to aggregate the data, you might be searching many millions of rows to find the transactions that belong to the cases of interest. Explore. Once you've gotten the data much closer to the form that you'll need, you've got to explore it extensively. At this point, the modeler is looking into data quality issues and identifying strong and weak predictors. This process must be done by the modeler and can't be delegated to others. So typically, some kind of data sandbox has been created. Prepare. Data preparation tends to be very labor-intensive. It's not just cleaning and formatting. The most important task is what's called feature engineering, when the modeler is experimenting with many different formulas to help make the predictions. The modeler has to be intimately involved, and it's highly iterative. Model. At this step, we use those fancy algorithms that are so closely associated with machine learning. One of the themes of this course is that folks worry too much about data volume during modeling. At this point, much of the hard work has been done, and the data sets have become smaller. This is rarely when data volume is the biggest issue. Scoring. Unlike modeling, which is done infrequently, scoring might be done in real time. It's got to be fast. Most pay too little attention to the speed requirement at this step and also forget a seemingly obvious but powerful point. Scoring is sometimes done on just a single record. Maintain. Folks also underestimate the challenge of this step. If models are going to be routinely refreshed and rebuilt, then you will probably want to automate the entire process. A lot of steps that were done manually at first now have to be transformed into a production step. So let's follow the data through the whole process. When the modeler begins, they're almost always starting by looking at lots of transactions. So for instance, we have a bunch of items that people have bought, and we can see that several rows are associated with one customer. What they're looking for at this stage is things as simple as how long is the maximum length of time a customer's been around? Do they buy just a few things or do they buy a lot of things? Because what we want to zero in on is the individual customer level. So here we're looking at just one customer, Mr. Streeter, who lives on Rockwell Lane. And what we have to now do is pull in all the transactions that belong to just him. So our data set is about to get shorter, but much wider. Let's see why. It's not just all those transactions that we're interested in, but all kinds of other things that we can get at that individual level. So we might have had hundreds of thousands of transactions, but associated with tens of thousands of customers. So again, a shorter data set, but made wider by all these facts about the customers that we're accumulating. we end up with something like this. So let's switch over to a churn example. And we can see that we have a data set that's got just one row per customer. And in this historical data, some conclusions been reached. We know that they either stayed loyal to our cell phone company or they churned. We're not done yet, though. What we have to do is a terribly important technical step. What the modeler now does is assigns about half of these cases at random to what is called a train dataset or a train partition. The other half is in the test partition. So what the modeler now does is builds the model only on the train data. In effect, our data size just got cut in half. It was massively reduced when we went from transactional to customer, and now we're building the model on only half of the customers. We do this so that we can validate our results against the other half of the data, the test partition. So now along comes a new customer. We've got to score them. We have to make a prediction for them. And again, this can be done on a single row of data. So we have the input variables, the predictors, but we don't know if they're going to churn or not, which is really the whole point of our modeling project. But what we can do is use that model that's been built and generate a score. And from that score, we can make a prediction. This particular customer has a 98% chance of being loyal to our company, according to the model. I want to revisit one of the themes of the course. Sometimes you'll actually discover that you have too little data. Years ago, the documentation for a software package that I sometimes use told the tale of the vanishing terabyte. The name alone communicates the basic idea. The data miner in the story was told that their client was terrified that their systems couldn't handle the volume. This occurred back in the 90s, by the way. Then they begin the actual act of choosing the relevant data, only to discover that they only had a few hundred instances of fraud. So what are some of the forces at play that causes your data to get smaller and smaller? One, not all the cases are relevant. So for instance, we've already seen that if you're going to market by email and you don't have everybody's email, the customers without emails might be left out. Another one, going too far back in history sometimes causes problems. Why? Well, 9 years ago, you might have had a very different business than you have now. Chances are good that you don't want to go back that far, so you're not going to use all the data in the data warehouse. Finally, we've seen that the modeler has to partition the data into train and test partitions. And we're also going to see that there's another technical step called balancing, which also can further reduce the data. So this phenomenon is more common than you think. You'll frequently find that you actually don't have enough data. So now we're going to cover some critical concepts that come into play whether your data set is large or small. So how much data is just enough? Well, let's say that you're trying to predict churn. A good rule of thumb is that you should have more than 1,000 cases that churned that you can use in training the model. But don't forget, you also need non-churns to compare them to. 1,000 of them would be helpful. And also, you need that test data set. Remember, we'll have our train and test partitions. So the minimum really starts to add up. It might surprise you how often you start to flirt with these minimums. Too little is more common than too much. So here you can see that to meet those very basic requirements, 4,000 is a nice round number on the low end. As you can imagine, 4,000 total isn't the hard part. Sometimes it's the 2,000 churns because they are more rare than the non-churns. We don't need to go deeply into the theory behind this, but many data scientists advocate having a third data set. It's a kind of double check, but we can see that while this can be helpful, it's tough if we're studying something like aircraft engine failures. We might not have 3,000 of those. So if you've got a little bit less, first of all, you almost certainly won't worry about the validation data set if you don't have your 3,000. You can live without that. The next thing that you can sacrifice if you're on the low end is you can keep the train data at 1,000 plus, but pull back a bit on the number in the test. And this, within reason, will work just fine. But now what do you do if you still don't have enough? If you have less than 1,200 churns, things start to get a bit more complicated, and the data scientist has to start looking into options. It can be done by starting to dip into their bag of tricks. Over the last 2 decades, this exact scenario has been present in at least 20% of my projects. It's not as rare as you think. What do you do if you're analyzing something that is highly out of balance? For instance, it's extremely unlikely that fraud represents half of our insurance claims. We certainly hope not. So, perhaps you've got 20,000 fraudulent claims, but over the same period, 2 million legitimate claims. The concept of balancing is forcing the numbers to be in balance by discarding, at random, some of the common cases. In this instance, legitimate claims are more common, so we discard some of them. I get into the theory of this in more depth in my Introduction to Classification course. For now, trust in the fact that the modeler does this fairly often, and they know how to do it, and they do it because it works. For now, let's attend to the following fact. We're suddenly down to just 40,000 cases, and we're only going to have half of those cases on our training data set. But don't you want to emphasize training numbers over testing numbers? Yes, that would indeed make sense to do. So, of course, with the million frauds, you don't worry about that. But with these numbers, we probably would make some adjustments. So, for instance, we could keep 16,000 frauds in the train and put 2,000 in the test, and if we wanted to, 2,000 in validate as well. Those numbers would be quite reasonable. So for our purposes, here's the punchline. No matter how we slice up train and test, whether we have validate or not, we're down to about 40,000 cases. Yet, we started with more than 2 million. Balancing probably affects about 1/3 of projects, so it has a major impact on sample size that is sent to those modeling algorithms that are very computationally intensive. This has a huge impact on the whole process. Now what I'd like to do is kind of invite you to watch my thought process as I assess a data set from the modeler's point of view. What this is going to do is give you an idea of why the modeler has to have access to such a huge amount of data in the early part of the process while they're trying to figure out what the final form of the data will be. The first thing we're going to do is focus in on the number of transactional rows per case. So let's take a quick look at some transactional data. Now, I may even do this visually at first, like I might look to see that this customer has just a few transactions, but obviously I'm combining this with queries. I can see this customer has many more. Here are some of the questions that I'm asking at this point. What is the maximum number of rows that I'm finding for any particular customer ID? And I might have millions or tens of millions of transactions that I'm looking at, or even more. I'm also curious if there are any case IDs that appear in my transactional data that are not considered active customers or vice versa. In theory, this shouldn't happen, but in practice, you discover those kinds of things. Then I want to get a sense of when I summarize the rows through aggregation, how I'm going to go about doing that and what information I might lose. For instance, turning back to this first customer, we can see that they bought things as expensive as $209, but there are also some purchases at $49. I'm not going to preserve all of those individual purchases, but I'm going to do something like a summation or an average, and I have to see how varied those purchases are, not just from person to person, but within each person. Also, do I want to separately pull the purchases they made with cash from the purchases that they made from credit card? By doing so, I would be making the data set wider, but what is the data telling me? Is preserving the distinction between those transactional rows going to be important for the analysis? Another one that's on my mind is the date range. Here in the data, it looks like this customer's transactions actually were all in 2015, Here we have a customer that has some transactions that go as far back as 2010. Again, it seems like we're searching for all these little details, but this is all helping us answer some important questions. Like, how far back do these transactions go? Can I look at just one calendar year and get the full pattern? Or will I be missing out if I only look at one calendar year? We're in the early stages of trying to figure that out, and that's why the data scientist has to physically look. They can't just have someone pull the data on their behalf. They have to look at this huge amount of data and start to sort this out. Finally, I'm curious about inactive rows. I want to look at my customer IDs and find out, are there some that had purchases way back in the past, but no recent purchases? If that's the case, they might be considered irrelevant to the current business problem, and perhaps I want to drop those. So that's just a taste of what I'm looking for when I do my initial assessment of the data. Now we're going to talk about what data we're going to use and what data we're going to set aside. I also discuss this in my Essential Elements of Predictive Analytics course, and there I go into a tad bit more depth and use a different example. So you'll recall that the whole purpose of building these predictive models is to generate a score that allows us to predict an end result. So let's revisit this notion that what we're trying to predict is whether or not a mortgage is going to be paid on time or someone might default. At deployment, we're going to let our new data flow through the model and we're going to generate a score. The rule for the data that we should include is really as simple as this. If it's going to be part of the scoring process, it belongs in the data. And if it's not going to be part of the scoring process down the road when we score future cases, it doesn't belong in the data set. A lot of times what folks will think is that they're adding bias to the model if they don't use all of their data. It's simply not true. The reverse is true. You want to only include those cases for which the model is relevant. So let's say that the reason that we're building this model is because we're going to proactively refinance folks that are at risk of default. Maybe some loans are not eligible for that refinance program because sometimes banks sell loans to other banks. Then it belongs to someone else. So even though we originated the loan, they're not eligible for the refinance program. Therefore, loans like that should not be part of the modeling process either. So when we go to grab our data, we should be very careful to select only the relevant cases. That way, there's proper alignment between the historical data that we use to build the model and the new data that the model is going to be used on. Now we're going to get into a topic that can become very technical and even somewhat confusing. But gosh, it's an important one. We have to talk about seasonality, the notion of a cohort, and time alignment. In the majority of projects, you're going to end up looking at a year's worth of data. Why? If you look at less than a year, there's all kinds of seasonal effects that you might not detect. For instance, if we were looking at a bunch of cell phone monthly statements, we have dads and grads specials in June, and we have Black Friday specials around the holidays, and we don't know how that's going to impact people upgrading their phones and changing their behaviors in certain ways. So looking at less than a year is risky. If a year is better than a month, why isn't 10 years even better than 1 year? Technologies come and go, phone plans get discontinued. Going back 10 years now, our data becomes very heterogeneous. So 1 year is often a balance between these two extremes. Let's take a closer look. We're looking at a bunch of monthly contract numbers that are coming in for a cell phone customer. And this is their non-contract spend. So notice that we get $0 fairly often. That's when they're just paying their contract amount and that's it. But in March and June and some other months, they spent more than the contracted amount. They ran out of data, or they bought something a la carte. We notice the same number popping up, and a subject matter expert could help us figure out what that is. But there's some kind of pattern here where in many months they spend the minimum, but in other months they spend a little extra. How are we going to figure out how this impacts something like churn? This customer, as it turns out, did indeed churn in December. So what are we going to do? How are we going to figure this out? And how does this shed light on how we're going to put our data set together? Well, here we go. We're going to start doing a bunch of calculations. Comparing recent behavior to baseline behavior is a very powerful way to get at what is going on psychologically in a customer's mind when they choose to churn. So we'll take the previous 3 months, we'll just call those the recent months, and their average extra spend is about $22. But over the previous 9 months before that, it was about $9 on average. So it's going to look something like this. For this one particular customer, we might have millions of them, but for this one customer, we compare their baseline to their recent, and we get a ratio. Gosh, that spend has kind of climbed just before they churned. And that may have had an impact on the churn event, especially when you think we might have dozens or hundreds of variables just like this. So far, so good, but here's where it gets complicated. We don't have only individuals that churned in December. We have individuals that have churned at all different times. In the data warehouse, in those monthly statements, these statements are referred to by the month. For us, the month is not the key fact about it. It's which months were just prior to the churn event and which baseline months were prior to that. Imagine doing this for millions of customers, tens of millions of monthly statements, all with different churn months. You can see how this gets complicated, and it's probably the most important example that we will see of why the data scientist has to be collaborating with folks in IT to decide how to handle calculations like this efficiently in production, but picking up on the characteristics that the data scientist finds in the data. For both understandable and appropriate reasons, most enterprise data management and data governance is designed around the typical user of enterprise data. When I attend and speak at the Data Warehouse Institute conferences, a lot of the specialists in the data warehousing area agree that about 80% of users of data are content with existing tables, data sources, reports, and dashboards. The other 20% need some kind of extra attention. Most of these same experts put data scientists in the top 1 to 3% in terms of their need for custom requests and access to unusual data. And it's worth pausing to ask why. As we've seen, they're often looking over long time horizons and should also be crossing departmental boundaries, pulling data in from multiple silos. No routine monthly or quarterly report is going to do that. Frankly, if they aren't at least considering unstructured data, they probably aren't trying hard enough at their part of the job. Granular requests will be common as well. I remember one of my favorite examples. On a churn project, I wanted the billing detail, which no one asked for, since the billing statement transactional history was really quite detailed. But I also needed unpaid transactional activity, like how often they sent or received a text on an unlimited plan, because only with that could I understand the psychology and behavior of the phone user. Unpaid transactions gave me insight into how they spent time on their phone. So if you're pulling 250 million transactions for 10 million phone customers, you might want the IT team to do that on a server on the data scientist's behalf. But the trick is that until the data scientist explores it, they can't be 100% certain of what they need. You'll still have to work together and try to be patient with one another. The data scientist ultimately has to explore the transactions file and has to explore the customer file that is produced when all those transactions are manipulated and transposed. On any project, there's going to be some surprises, and those surprises may prompt you to have to pull the data and transform it again. If this happens 24 times, then the data scientist is probably new in their role. But even the most veteran modeler may have to make adjustments and pull the data more than once. It's one of the trickiest stages of any modeling project, getting all the people and all the machines working together to pull that data that's going to graduate on to the next steps, data prep and modeling. In my experience, some of the most important variables get generated when you convert a very tall transactional data set into a case-level data set. But you lose a lot of information when you go from a lot of rows to fewer rows. So what kind of information do you want to keep? A lot of this will seem obvious, like you might do total purchases or median or mean purchases. What might be less obvious at first is it won't be clear to the data scientist which of these variables is going to work best until they're in there assessing and exploring the data. So for instance, somewhat famously in statistics, means are sensitive to outliers. The presence of just a few outliers can change the mean, but it doesn't change the median as much. Now, an experienced data scientist will just grab a few of these, but there are some that they won't know about until they look. For instance, looking for something like the number of transactions under $5 is not something that a data scientist chooses to do because of statistical theory, but because they find something unusual in the data that they want to further explore. You also have to restructure. So you don't want to take what could be hundreds of transactions for an individual person and summarize them in just one or two numbers. Sometimes you'll want to do that for each department or category in which they've made purchases. Think about Netflix. Most of us use Netflix as a service to watch movies. If all we did was the total number of minutes that we watch Netflix in a calendar year, that's not going to be nearly as powerful as if we break it down into documentary minutes, comedy minutes, horror minutes, and so on. And this is what we mean by restructuring. Dozens, if not hundreds, of variables will come from this process of aggregating and restructuring. Now we're going to take a moment to talk about an aspect of data preparation which might at first seem like a minor technical detail, but pretty much everyone who's involved in the project, both the modelers as well as the folks that are helping provide and prep the data, need to know about this. It's called dummy coding. So let's say you're making a prediction and one of your predictors is employment category. So here we've got folks on salary, we've got some independent contractors, some part-time wage, and some full-time wage. In general, what we're going to do now is we're going to transform this so that whenever they are true in a particular category, they're going to get a 1, and otherwise they're going to get a false. So again, we've got 4, salary, IC, we'll call it, part-time, full-time. What does that end up looking like? It ends up looking like this. So our original variable had 4 categories, and now we have 4 new variables. Salary, yes, no, which is true or false. Independent contractor, yes, no, and so on. Okay? So why do you have to know this if you're in a data prep role or perhaps in an IT role? Isn't this something that the modelers just worry about? Here's why it's important. A lot of modeling software will automate this internally. Sometimes even the modelers don't notice that all of this is going on because the software will just do it. So then when you go and put the model into production and you're generating scores, you go, where did this FTW variable come from? We gave it a variable employment category, and now we have these other variables. Who made them? Where are they? This is critical if you're going to take the model out of one software platform and carry it over to something else. What if you built it in a commercial package, but you're going to deploy it in SQL? You have to know that these were generated behind the scenes so that you can score and deploy the model correctly. Pretty much everything we've been talking about in regards to data preparation is a kind of feature engineering. Now, the cross-industry standard process for data mining likes to call this data construction. But the more common term these days is feature engineering. What it basically is extracting the meaning out of variables by using a whole bunch of different formulas. So we've already seen that we might calculate a ratio or a delta comparing recent behavior to baseline behavior. We generate all kinds of variables through aggregating and restructuring. But once it's already in its basic form, 1 row per customer or 1 row per patient, 1 row per loan, we're still going to continue doing formulas. Let me show you a couple of quick examples. Dates, for instance, are not very useful to these predictive models, but the gaps between dates is very interesting to modeling. So we're going to be doing what's called date arithmetic. You also might extract a fact about a date, that it was a day during the business week as opposed to on the weekend. You might also be extracting information from a whole host of codes and IDs. For instance, the second character in a VIN number is how you figure out the manufacturer of the vehicle. Finally, a lot of folks think of text mining as a kind of modeling, and it's reasonable to say that, but you can also think of it as a kind of data prep, because in an instance like this, the customer said my bag was lost and I still had to pay a bag fee. We're extracting that fee concept and we're creating a Boolean variable that says that for this customer, fee concept was true. So it's also a kind of feature engineering, and we might generate hundreds of variables just like this that are generated through text mining. So just to give you an idea of how terribly important this is, let me tell you about a project that I did a few years ago and just the volume of variables that we did in this way. We ended up generating more than 800 variables that we considered for inclusion in the model. Of those more than 800, only 60 were pulled directly from the data warehouse. So therefore, more than 700 had been engineered by us. The final model used about 80 variables, which is actually quite a bit in a model. Of those 80, only 6 were pulled directly off the data warehouse. So all of the critical variables, or nearly all, had been created through feature engineering. The reason all of this is so critical to our current discussion is that all of these calculations are eventually going to become part of the scoring and deployment process. I've mentioned that I think that most folks overestimate the scaling concerns regarding the modeling phase. I want to walk through the modeling phase from the point of view of the modeler to put that comment into proper context. The beginning of the modeling phase, an organized modeler should have a list of all of the different algorithms and settings that they're going to try. Now, I wanted a manageable list for our purposes here, but keep in mind that the list would be several dozen and very possibly over 100 combinations of algorithms and settings. So let me give you a sense of the kinds of things you'd be experimenting with. You'd certainly do more than one algorithm. Most modelers are going to have access to many of these. Here I've listed CART, support vector machine, neural net, and logistic regression, but there are many others. Then the modeler is going to be changing settings as well. So for instance, in support vector machines, there's something very technical called the regularization parameter. And they call this kind of thing changing the hyperparameters. But you're going to be changing these settings. There's going to be a bunch of those. Then we've talked about balancing in this course. The modeler, though, if they're being diligent, is going to try data that's been balanced and very possibly data that has not been balanced as well. And they're going to have the skills to know what to experiment with. But the decisions here should be made empirically and not from some theoretical basis. You just try and try again. Then some algorithms are better at using all the variables, and other algorithms benefit from the modeler choosing the best variables first and then running the algorithm. So you have to experiment with this. Ultimately, what's happening is these 80 or 100 or 120 attempts are all being ranked on train and test accuracy, and the modeler knows how to do that. So what is critical for us in this course? Does it matter if this is running overnight? Does it matter if you write a little bit of a loop in your code and you're trying 10 different values of C in your support vector machine between when you leave for the evening and come back to the office in the morning? The answer in short is that it doesn't. So the reason that you really don't have to worry about scalability in the modeling phase unless you get to huge numbers is it doesn't matter that much if the model takes a half hour or an hour or even a few hours to run, because you're only going through this process once. Where you have to worry about these algorithms is during scoring, and then you have to worry about them again during model rebuilding, both of which we will talk about. Now we're going to talk about 3 reasons why some algorithmic approaches are much slower than others. The first is that some modeling algorithms, they tend to be of the machine learning style, perform brute force calculations. Let me show you what I mean. This is a tiny little data set, but we're trying to predict whether or not an expected mom is going to have a low birth weight baby. If we use a statistically based approach, what it's going to do is only perform about a dozen calculations or so, between a dozen and 2 dozen. Specifically, what it's going to do to figure out that cut point between lower risk and higher risk is 107 pounds, is it's going to break all of the expectant moms into deciles, less than 100 pounds, going all the way up, with the highest one being over 171 pounds. Then it's going to perform a calculation on just those 10 groups to decide where that cut point should be. If we're using a machine learning technique on the very same data, it's going to use a brute force approach. It's going to take every single expectant mom and rank them from lowest to highest weight and try all possible cut points. So if you were doing something like predictive maintenance on machinery and you had heat or pressure being measured to 3 decimal places, every measurement might be different, and you might be comparing tens or hundreds of thousands of measurements on very large data sets. So this can be a difference of an order of magnitude or 2 orders of magnitude in terms of speed comparing the 2 groups. Here, you would never notice the difference, and up to 1 million rows of data, you would probably never notice the difference, but at high levels, you would. The second reason that some algorithms are much slower than others is some algorithms just perform more calculations. Let's take a look. This is an artificial neural network that's been built on the same data set. All we're trying to do is predict whether or not an expectant mom will have a low birth weight baby. Now, artificial neural networks get quite technical, but take a look. I just want you to attend to the very large number of lines. So if we were using a statistically based approach, we've only got 3 variables here: weight of the mom, uterine irritability, and hypertension. So a statistical approach would only do 4 calculations, 1 per variable and what's called the constant. But the point is there'd only be 4. But look at all these lines, many, many more. So the neural net is doing many more calculations. That makes it more accurate, but it makes it slower. Over here, we've got 6 times 5 lines. And yes, indeed, there's a relationship between the number of shapes on the left and the number of shapes in the middle. And over here, we've got 6 times 2. So the traditional technique would have just 4 numbers that have to be fit, what's called coefficients. The neural net's got 42. On data sets of a couple 100,000 or 1 million, even a couple million, you're not going to notice the difference. But if you've got very, very large data sets, you will start to notice the difference between the number of calculations that have to be performed. The third reason why some algorithmic approaches are going to be slower is we literally build more models in some cases. So for instance, going all the way back to the 80s, it was proposed that we could build more accurate decision trees if we simply built a bunch of them and then averaged. That's called bagging. But over the years, a number of new algorithms have been developed that capitalize on this same idea. Somewhat famously, there's one called random forest. More recently, there's a fancier one called XGBoost. But all of these do that same basic notion. They build lots of trees and then average them. So think about this now. If you're going to build 50 trees and average them, you know that your computational time is going to be about 50 times more. That can start to catch up with you. There's a completely different sense in which we could talk about building more models. Let me give you an example. Years ago, I was running an analytics team, and one of the big projects that we did was building models for each SKU, so each bike model of a bunch of children's bikes. There were tens of thousands of them, but we also had to build a model for each style of bike at each store location. This was particularly important to get right at Christmas because this company sold a large fraction of its total sales during Christmas time. So picture that now. You've got tens of thousands of SKUs, and you've got hundreds of store locations. Let's say that you chose an algorithmic approach that was 10 times or 50 times or 100 times slower than a statistical approach like logistic regression. If you only had to build one model, go for it. That added accuracy is going to be very helpful to you. But we're building hundreds of thousands of models. Under these circumstances, you might choose to use a technique, even if it was a tiny bit less accurate, if you could build this more efficiently, especially if you're going to rebuild these models every month. So on that particular project, a great choice turned out to be logistic regression, which does indeed turn out to be one of those statistically based techniques. But for that project, it was the right choice. Now we're going to talk about sampling. I find that a lot of folks are afraid to sample, and there's really no need to be. First, in most projects that I do these days, I don't have to worry about sampling because the models will run in just a few minutes, even if I have 5 or 10 million rows. Now, you get up into tens of millions, it might take 15 or 30 minutes, but you'd be surprised how quickly these models will run. Secondly, folks are afraid it's going to introduce some kind of bias. It doesn't tend to, and with these techniques I'm about to mention, you can eliminate that concern. First, there is a mistake that some folks make that is easy to avoid. Let me explain. If you're looking at my credit card transactions, it's okay that I'm not included in the sample of customers that you chose to look at. But if I had 81 credit card transactions last year, you don't want to sample the transactions because then when you calculate number of transactions for me, you won't get the correct number, 81. So make sure that you're sampling people, cases, insurance claims, not the transactions that belong to those cases. Also, and this is such an easy trick, sample temporarily. Let's say you're going to run 120 different algorithmic variations, algorithms, settings, balanced or not, and so on. This is so easy, folks. Just go ahead and take a 10% sample, run all 120 of your algorithmic variations on that, identify the top 5 or 10, and then run those on all the data. You have saved hours or days of processing time, and you've lost almost nothing. Because on a 10% sample, the accuracy that you're going to get is still going to be correct to a few decimal places, and you're still ultimately running all of the data. So it's easy and harmless. Finally, you can just be a little creative. We know that we divide our data into train and test and sometimes validation data sets. Does that mean that we always have to do 1/3, 1/3, 1/3? Of course not. Why not go with 20% train, 40% test, and 40% validate if you happen to have 150 million rows? That will work just fine, but you've massively reduced the amount of data that's going through the computationally intensive phase, but you're still utilizing all the data. Now we're going to talk about a topic that could easily warrant its own course, modeling with missing data. But we're going to try to stay laser focused on the topic at hand, which is the implications of the decisions that we make throughout the entire process with a particular focus on scoring and deployment. You've got to be deployment focused. 100% of the time, there's going to be some missing data. Then what happens in most projects is the modeler has to fix it and clean it so that it's not missing. But then at scoring, it's missing again. Everybody has to work together to ensure that the model will work at scoring. Modelers, especially if they're statisticians, are trained to repair and address data issues. This is a critical skill to have on the team, but don't forget to ask yourself if the data even belongs in the model. For instance, before the mortgage crisis, a lot of small real estate investors could get so-called no-doc loans, which got that name because they didn't have to submit all of the usual paperwork. If they could show good credit, then they didn't need detailed income documentation, and that documentation could be waived. No one grants those loans anymore, though. So, if that kind of data is systematically missing, and you figure out why, then they probably don't belong in your brand new loan model anyway. The reason we worry about these issues is that if you fix the data during modeling, but then it's missing at scoring, whatever fix you introduced, you have to carry over to the scoring process. A technique that all modelers learn is imputing. It's replacing a missing value with an estimate of its value. Sometimes software will even do this automatically, and it can get quite elaborate. But what if your deployment platform is different from your modeling platform? Too often, modelers get caught up in the modeling process and don't think ahead to deployment. Whatever imputation strategy you choose, including not doing it at all, has to work during scoring too. One of my favorite solutions to this is just being creative about it, and you can potentially make the issue go away. Let me explain. It's important to remember that what we're doing during modeling is more like inventing a helpful device, like a light bulb or a vacuum cleaner. It's less like discovering the laws of gravity. In other words, models aren't right, they're reliable and useful, or not. So one of my favorite tricks is making the missing data go away, and this makes it deployment friendly too. One of my favorite examples of this was on a cell phone project. We dealt with missing data by building 2 models. The problem we had was a big percentage of customers were on their first contract, so all of our prior contract variables were missing, and there were a bunch of them, and they were good variables too. Imputing would have made no sense in this context, so we built 2 scoring engines, one for new customers and one for established customers. It wasn't overly complicated, it got the job done, and at scoring and deployment, all we had to do is score 2 models instead of 1, so it worked great. There's a good reason why traditional machine learning methods have stood the test of time. They still work quite well, and they tend to be highly scalable. Let's take a look. One advantage of these more traditional techniques like logistic regression, let's say, or decision trees, is that they're very transparent. They really tell you a story about the data. Also, they're fast. They're fast models to build, generally speaking, and they're fast at scoring. Also, super important to us in this course, they're easy to migrate. These are straightforward formulas. So it's not ridiculous even to contemplate manually moving it from one system to another or writing a simple parser to do so. For all these reasons, they are still among the most common choices. They might not be the newest or the most exciting, but they really do work in many situations. Let's go a level deeper. Our statistical models, again, like binary logistic regression is a super common one, are going to produce algebra-like formulas. They're going to have as many of those coefficients as you have variables. So even 50 or 100 variables in your model, it's not cumbersome to migrate these. Decision trees, little bit different, but have the same benefits. They have a simple if-then structure. They generate rules, and they're going to have as many rules as subgroups produced by the model. So if you divide your cases into 30 risk groups, you're going to have 30 if-then statements. Let's take a closer look. Now, I know this formula looks a little intimidating at first, but it's really not so bad. What you want to be looking for is that one coefficient per variable. So, for instance, weight gets its own coefficient, premature labor gets its own coefficient, also hypertension, and then something that we just call the constant. But the bottom line is we have 3 variables and 4 of these special numbers, which we have to use in our formula. Any modeler that chooses to use logistic regression is going to be familiar with how this formula works. Now let's take a look at decision trees. Same data set. If the mom's weight is greater than 106 and she does not have hypertension and her age is less than or equal to 27.5, the model's going to tell us that she's predicted to have a healthy weight baby. Now don't forget, both of these techniques are also generating scores. So they're making a prediction, but there's also a score. But in order to migrate this to another platform, all you have to do is familiarize yourself with either the algebraic-like formula or the format of the if-then statements. What about scoring black box models? So-called black box models are just models that have gotten sufficiently complex that it becomes extremely difficult to tell a story about your model. In other words, you can't really interpret it very easily. Now, black box models are often very accurate, and they come in multiple forms. This artificial neural net is just one of many models that falls into this category. What people like about them is they can be incredibly accurate, but they have some disadvantages that we have to mention here. Now remember, each line in this diagram represents a coefficient, so they're getting quite complex. That also means that getting your black box model out of one platform and into another can be a challenge. So if you're building the model in one piece of software but then deploying it somewhere else, you have to deal with that. One great way to do it is using something called Predictive Model Markup Language, or PMML. Now, this has been around for many, many years, and the corporate members of the data mining group, which involve many of the important companies in this space, collaborate on PMML so that you can get these complicated models out of one software package and into another one. Now, if you're particularly interested in this aspect of it, or in the technology around deployment, you're going to want to check out Dan Sullivan's course right here in the library called Deploying Scalable Machine Learning for Data Science, and he mentions PMML in the course. Something you're bound to hear about, because artificial intelligence is a really hot topic right now, is deep learning. What deep learning is very complex artificial neural networks. In fact, what makes it deep is that there's more than one hidden layer. So check out this diagram. Isn't it remarkable how many lines there are? So deep learning models are built on hundreds and hundreds of millions of rows, generating hundreds of thousands of coefficients, and have to be built on special computers. The good news is that for most folks, you're dealing with everyday business problems, and you're not going to have to worry about speech recognition and driverless cars and so on, which are the big application areas for deep learning. Most of us facing everyday business problems within organizations are going to be able to get by just fine with models that are somewhat less complicated than deep learning models. If you're curious about deep learning, there are some fantastic courses about deep learning right here in the library. So what about scoring ensemble models? Ensembles are really hot right now, so we'll want to talk a bit about the implications of choosing an ensemble when it gets to scoring. What ensembles are is a collection of models. It could be just a handful. It could be as many as 40 or 50. They come in all kinds of different styles. But remember that the way that this is going to work is you have to build the individual models, and then you have to combine them in some way. And sometimes you combine them by simply performing an average, or another option has been doing especially well in data mining competitions recently, and it's called stacking. You build multiple models, and then there's another model on top which takes the predictions of the first models as input and then produces your final prediction. They're really something, and they perform very well. That's why they're always among the top performers in these predictive analytics competitions. But a bit of a cautionary note. Clearly, if you're building 5 models or 10 models, then your scoring is going to be 5 or 10 times slower. The Netflix prize is very informative here. Years ago, Netflix offered $1 million to the team that could do the best job improving their recommendation engine. And you may have heard the story. The winner was never deployed because the winner was a very complex ensemble of dozens of underlying models. And it was too slow at runtime. So even though that was the team that won the $1 million, it was the second place team that actually saw their model deployed because it was faster in a production environment. Now we're going to talk about batch scoring versus real-time scoring. We're going to have a particular focus on when to choose each. I think we're all familiar with the basic concepts, but let's do a couple of examples. The classic real-time scoring situation is something like credit card fraud. A transaction is run, and you need near instant feedback. As a business traveler, not infrequently, I will get a text message from my credit card asking me if a particular transaction was legitimate. The classic example of batch scoring is traditional marketing campaign models. Now, of course, back in the day, and this was one of the earliest applications of these techniques, you would send out a mass mailing, but only to those individuals that had a high score. Now it's more often email, but clearly what you're doing is you're doing the entire campaign, choosing the list, and then sending out the emails. It's not as black and white as it first seems, however. Let's contemplate an inbound call center situation. Let's say, for instance, that someone's calling in to their cable company and they're asking about an upgrade, or maybe they even have a repair issue or something like that. Maybe what we do is we take their churn score into account. But here's the issue. Most people don't make a distinction between the following two events. When did you generate the score, and when did you retrieve the score? So in the call center, they might offer a discount because this individual has a high churn score. They've run into trouble with their account in the past, and we want to keep them as a good customer. But that doesn't mean that when the call center employee hits the enter key, that generates a new score. You may go that route, but you also could choose to generate the score in batch, but simply retrieve it when the call center operator needs it. There's a huge difference in cost between these two scenarios. So which should you choose? Well, look into that increase in cost. And folks, it's not trivial. It's hard to generalize, but this is going to be several times more expensive to do real-time models. It's just a lot more complicated in terms of infrastructure. That doesn't mean that it's not going to be the right choice in some situations. Is it mission critical? In my experience, most clients that I meet for the first time only go this far. Do we have the budget? Is it mission critical? If so, it's presumed that real-time is always better than batch. But there's other things to consider. How often do the variables change? I meet so few individuals that take the time to ask this question, and it's such an important one. For instance, years ago, when I was on a cell phone churn project, virtually all of our variables came from monthly statements. Since the variables only changed once per month, it didn't make a bit of sense to do nightly scoring, because you could know in advance that the scores were not going to change until a particular customer's billing date had arrived for the current month. You also want to ask, what's the increase in accuracy? At first, you might think this is an intangible. It is not. This can be measured. If you have variables that are changing monthly, but other variables that are changing daily, you build the model with only the slowly changing variables. Then you rebuild the model with both the slowly changing and more quickly changing variables, and you can measure the difference. This can be quantified. Finally, what's the natural rhythm of the business? I've been on a number of insurance fraud projects, and think about what's happening. A list of cases is passed on to an investigative team. These are folks that are physically driving around in cars, taking pictures, asking questions, and so on. This is not something that happens like the credit card transactions we just spoke about. Therefore, doing this as a weekly batch or even monthly batch probably fits the rhythm of the business just fine, because if you were updating claims in real time, it would have no direct impact on the behaviors of the investigative team. It takes a while for them to do their part of the job. Therefore, batch is perfect. Now let's talk about data prep and scoring. Let's revisit the monthly statements. I want to discuss in some detail how this worked on an actual project. At this particular client site, there were 8 different billing statements. So customers would get their monthly billing every couple of days. Some folks got it on the 4th, some on the 8th, and so on. So on the evenings that those monthly statements were about to go out, all of those new billing variables were calculated. And an hour later, at 1 a.m, all the data preparation was done. So what those calculations were all the feature engineering that the modelers had prototyped during the modeling phase and that they ultimately used in the model. And then 1 hour after that, at 2 a.m, the scores were calculated. So what folks often forget to take into account that scoring is not just about the model, but also about all that data preparation that generates the variables. After all, it's usually the feature-engineered variables that are used in the model more often than raw variables. Once those churn scores were in place, they were now tied to the customer ID and were used as ingredients in numerous calculations until the next billing date. Now I want to talk about some issues that come up when you're trying to get all of that data preparation ready as it moves from modeling phase to production. First, not all the variables are used. Remember that hundreds of variables are considered for inclusion in the model, but usually only dozens of them are actually used. Not all formulas were built for speed. When these formulas are first put together by the data scientists and the statisticians, they're focused on model accuracy. They're not worried about efficiency at that precise moment. They might have to be translated into another language or possibly rewritten. Also, historical data is not identical to scoring data. For instance, in preparing for the model, you might check to see if there are any customer complaints in the 30 days prior to a churn event. Now that we're scoring, there is no churn event. That simply becomes last month. So they're similar, but not identical. Finally, sources that were ad hoc during the modeling phase have to be made more permanent. For instance, on this very same client example, I didn't have direct access to drop calls because that was part of the cell tower data, not the customer service data. Once we identified that that variable was going to be in the model, more ready access was made to that data. Here's the bottom line, folks. Moving all that data preparation code from the form it was in during the modeling phase to the form it needs to be in for scoring and deployment is a non-trivial event, and you have to work together to make it as efficient as possible. Now let's revisit the call center example and see if there are circumstances under which we would definitely want real-time scoring. For instance, let's say someone's calling in around a cell phone repair or possibly even an upgrade, and they've had 3 complaints over the last 7 days. It would certainly seem inappropriate to not take that recent activity into account if we can. So what would be the most efficient way to do so? This is what people forget. We can actually do a mix of batch and real time. So we can do our standard model, which is taking our billing data, only updated monthly. We can run it through our model, and we generate our churn score. Keep in mind that this model is using dozens of variables. The data prep takes several minutes to run. It's run in batch. The system's already there. We want to leverage this, not rebuild it. So this is what we do. We take that churn score from the first model, and we simply add to it only those things that change between billing statements. Visits to the physical store, calls to the inbound call center, repair events, complaints, that kind of thing. This could be as few as a handful of additional variables. So we use the score that uses dozens of variables. We add a few more, and that gets fed into a second model. Since it only has a handful of variables, it's going to run quickly, and the data prep associated with it is going to run quickly. And then we get an adjusted score. If I was asked by a client to do real time in a call center, this is exactly the kind of approach that I would recommend. The cross-industry standard process for data mining describes monitoring and maintenance in the following way. They're important issues if the data mining results becomes part of the day-to-day business in its environment. A careful preparation of a maintenance strategy helps to avoid unnecessarily long periods of incorrect usage of data mining results. I want to elaborate on this in a little bit more detail and then provide a case study. Some other considerations that ChrisDM provides. When should the data mining result or model not be used anymore? Identify criteria. Here's the important stuff, folks. There's some threshold above which or below which we start to worry about the model, and you want this determined in advance. Things like accuracy, also changes to the environment. It could simply be that the business goal that we had is no longer there. What should happen specifically if the model or result can no longer be used? Will the business objectives of the use of the model change over time? All of these will eventually happen, but somebody's going to be minding the store. So to put this into a little bit of perspective, keep in mind that let's say you had an external modeler that was involved, somebody that came in from outside to help you build the model. They're almost certainly not around at this point. The project manager that was assigned to this project is no longer there. You've got to have a team member. They tend to be a more junior member of the team that's just going to invest about an hour a month, but indefinitely, to look in and double check the model and then report to others if these events have started to occur. Now, if you want a more philosophical take on model monitoring, in Tom Cabaz's 9 Laws of Data Mining, he talks about the law of change, and I discuss the law of change in my Essential Elements course. I want to now share an example, which unfortunately is an example where monitoring was not done and it started to cause problems. So I was invited in to chat with a manufacturer who wanted to completely rebuild their forecasting model. Now, this model had taken many weeks, in fact, almost certainly months to build. It was only about a year and a half old, and a complete rebuild would have been quite expensive. So the question that I asked them was the following. Could you tell me what the accuracy has been like from month to month? Was this a poor model from the very beginning? Did it degrade over time? How would you describe the change in accuracy over time? Well, and unfortunately, the answer was that they didn't really know, but that the sales managers who are responsible to provide product to clients, but also to communicate what the demand was for parts in the factory, were increasingly vocal about their disappointment in the model. But there was nothing tangible about it. It hadn't been quantified. This is what you would be looking for each month. Here's an instance where the percent accuracy, now remember these were forecasts, so the forecast might be a percent or two too high or too low. You could imagine something like what is called a MAPE in statistics, the mean absolute percent error. You're simply measuring that error. Is it stable? This chart looks like it's been fluctuating over time, but what if you saw something like this? It starts to creep up, and now for quite a few months in a row, it's consistently above 2% error, where it was more like bouncing around 1.5% error. This is exactly what somebody should be watching, and when you start to notice this happening, now you bring the team in, the IT folks and the data scientist and the internal customer all assemble again, and you start asking whether or not the model needs attention. But if you fail to monitor it month after month, you won't know this is happening, and then you'll suddenly have a crisis on your hands. So how often should you rebuild your models? It's an important question to ask because it has major cost implications for the cost of the project. One of my favorite examples of this is luggage fees. When I first started traveling heavily many years ago, the whole way that we handled luggage as business travelers was very different. Most people checked their bags and there usually weren't luggage fees. Now, checking bags is rare and luggage fees can be high. So, I think I'm stating the obvious here. Any model that was talking about business travelers and their loyalty is going to be changed, perhaps dramatically, by the addition or subtraction of variables like this. So clearly we need to rebuild our models. The question is how often, because if we do it more often than we need to, we're spending infrastructure dollars where we don't need to spend them. How do we think through our decision? Well, let's be clear about what our options might be. Let's say you're going to rebuild infrequently. You might have a situation where you're content with monthly scoring and annual rebuilding. Well, if you're only going to rebuild the model annually, and you've got a data scientist on staff, you might decide to do an annual rebuild. There are some wonderful advantages of manual. You can think about things like changes in the business problem in a way that automated models can't do. Now, I'm not saying that you always go this infrequent, but think it through. Make sure you're making the right choice for you. What about much more frequent? How about real-time scoring combined with somehow automatically building the model every night? Now, one could do an entire course around automatic rebuilding, but think about the cost implications. This scenario would probably be 5 to 10 times more expensive than the infrequent rebuild scenario with the manual rebuild. What are some things to think about when you're choosing between these two extremes I've proposed, infrequent and frequent, obviously with shades of gray in between. First question to ask, what's the potential increase in accuracy? As we've seen before, this is not an intangible. You should be able to measure the actual increase that you get by rebuilding the model. You could even do A/B testing, where the data scientist on the team rebuilds the model a month later and you check to see how much things have changed. What's the increase in cost? This too is not an intangible. You should be able to measure this. Critical question, how often do the underlying relationships change? This is different than asking how often do the underlying variables change. We're asking how often the underlying relationships change. Let me clarify this with an example. I once heard a member of a deployment team talking about how they were going to start moving towards more rapid rebuilding. And I was very curious why, because these projects are expensive, and I'm always very curious to hear client justification around this, because it can be a very powerful thing when it's done right. His answer was, let's say that you are with a healthcare provider. You want to make sure that your latest measurements, like blood pressure, are in the model. We didn't talk at length that day, but I've often remembered this conversation because think about it. Having the most recent blood pressure measurement does not affect the rebuilding of the model. It affects the score. Changing attitudes around something like luggage fees affects both the score and the model. Make sure you're not confusing the two, everybody, because rebuilding models more frequently than you need is very expensive indeed.